In a typical electrical distribution system, a neutral conductor provides a reference point for grounding and balancing the voltage of the three-phase lines. However, in certain applications, such as industrial facilities with large three-phase motor loads, a closed delta system without a neutral is sometimes used. In a closed delta system, the three phases are connected in a loop, or delta configuration, without a neutral connection. This type of system is used when the load is primarily composed of three-phase motors, which do not require a neutral for operation. If the power company supplied a farm with a closed delta system, it may be due to the nature of their load, which is typically three-phase motors. The absence of a neutral is not uncommon in such systems. Even in a balanced closed delta system, there can be a slight voltage imbalance between the three phases, typically due to differences in load or line impedance. This imbalance can result in a voltage appearing on the center tap of the generator, which is connected to the ground grid of rods. In a closed delta system without a neutral, grounding is typically achieved through a ground rod system. The rods provide a low resistance path to earth for fault currents and any other stray currents that may flow in this system. If a fault occurs, the current will flow through the ground rods and back to the power company's grounding system. While the grounding system is designed to protect against faults, there is a potential concern about stray voltage if the ground grid is not properly installed and maintained. Stray voltage is unwanted voltage that can appear in the soil or on equipment due to current leakage or imbalance. This voltage can be harmful to livestock and can interfere with electronic equipment. Therefore, it's essential to ensure that the ground rod system is properly designed, installed, and maintained to minimize stray voltage. Monitor the system regularly for any voltage imbalances or ground faults. Consider consulting with a power company and an electrical engineer to review the system and address any potential safety concerns. Also, observe the behavior of the cows and report any unusual behavior to the power company and the electrician. To further elaborate, let's delve deeper into several aspects of this electrical setup. Firstly, let's discuss the closed delta configuration in greater detail. Imagine a triangle, each point representing a phase A, B, and C. These phases are interconnected in a loop. The absence of a neutral wire means there's no direct connection to the center or common point of the power source. This setup is particularly efficient when powering balanced three-phase loads, like large motors, because these loads inherently distribute the current evenly across the phases. However, challenges arise when dealing with single-phase loads. That's why a step-down transformer, connected to two legs of the delta, is used to supply lighting and receptacle loads, converting the 480 volts three-phase power to a more usable voltage like 120 volts or 240 volts single-phase. This allows for the operation of common appliances and lighting systems. Secondly, consider the grounding system. The installation of 10 ground rods in a large loop is a critical safety measure. These rods provide a low impedance path for fault currents to return to the source, which is essential for the proper operation of overcurrent protection devices, like circuit breakers or fuses. When a fault occurs, such as a live wire coming into contact with a grounded metal enclosure, the fault current flows through the ground rods, tripping the breaker and disconnecting the power, thus preventing electrical shock hazards. The effectiveness of the grounding system depends on several factors including the soil resistivity, the depth and spacing of the ground rods, and the quality of the connections. High soil resistivity increases the resistance of the ground path, reducing the effectiveness of the grounding system. Thirdly, the voltage imbalance in a closed delta system can stem from several sources. Differences in load distribution across the three phases can cause unequal current flow, leading to voltage variations. Line impedance, or the resistance and reactance of the conductors, can also contribute to voltage imbalance. Long cable runs or variations in conductor size can result in different voltage drops across each phase. Generator characteristics can also play a role, with slight differences in the output voltage of each phase. These imbalances, even if small, can create a voltage on the center tap of the generator when connected to the ground grid. This voltage, if not properly managed, can lead to stray voltage issues. Fourthly, let's address the potential concerns related to stray voltage. Stray voltage is a low-level electrical potential that can exist between 2 points, such as the earth and a piece of equipment. It's typically caused by current leakage from the electrical system, often due to poor insulation, faulty wiring, or inadequate grounding. In agricultural settings, stray voltage can affect livestock, particularly cows, causing behavioral changes, reduced milk production, and health problems. Cows are particularly sensitive to stray voltage because they often stand on wet surfaces which provide a good electrical connection. Even small voltages, in the range of a few volts, can be noticeable and disruptive to them. The grounding grid, while intended to mitigate fault currents, can also become a pathway for stray voltage if it's not properly designed and maintained. Corrosion, loose connections, or improper installation can increase the resistance of the ground grid, making it less effective at dissipating stray voltage. Fifthly, let's consider recommendations to address these issues. It starts with ensuring that the ground rod system is properly designed, installed, and maintained. This involves selecting appropriate ground rod materials, driving them to the correct depth, spacing them adequately, and making sure that all connections are tight and corrosion resistant. Regular inspections and testing of the grounding system are essential to identify and address any problems. Soil resistivity testing can help determine the optimal number and placement of ground rods. Monitoring the system regularly for voltage imbalances and ground faults is also crucial. This can be done using voltage meters and ground fault detectors. If significant imbalances or faults are detected, further investigation is needed to identify and correct the underlying causes. Consulting with a power company and an electrical engineer is highly recommended. They can provide expert advice on system design, grounding, and stray voltage mitigation. They can also conduct a thorough review of the electrical system to identify any potential safety concerns and recommend appropriate solutions. Observing the behavior of the cows and reporting any unusual behavior is also important. This can provide early warning signs of stray voltage problems. If cows are exhibiting signs of discomfort, such as reluctance to drink water or enter certain areas, it's essential to investigate the possibility of stray voltage. Furthermore, proper wiring practices are essential to minimize the risk of stray voltage. This includes using appropriately sized conductors, ensuring proper insulation, and avoiding ground loops. Ground loops occur when there are multiple ground paths between two pieces of equipment, which can create circulating currents and increase the risk of stray voltage. Regular maintenance of electrical equipment is also important. This includes inspecting and tightening connections, replacing worn or damaged wiring, and testing the operation of overcurrent protection devices. A preventive maintenance program can help identify and address potential problems before they lead to stray voltage or other electrical hazards. Additionally, consider using isolation transformers to isolate sensitive equipment from the electrical system. Isolation transformers provide a high degree of electrical isolation, which can help prevent stray voltage from affecting sensitive equipment. In addition to the technical aspects, it's also important to communicate effectively with the power company and the electrician. Open communication can help ensure that everyone is aware of potential problems and that appropriate steps are taken to address them. Keep detailed records of all inspections, tests, and maintenance activities. These records can be valuable for troubleshooting problems and for demonstrating compliance with safety regulations. The goal is to create a safe and reliable electrical system that minimizes the risk of stray voltage and protects both people and livestock. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding of electrical systems. Article 250 covers grounding and bonding. It's essential to comply with these requirements to ensure the safety and reliability of the electrical system. Specifically, NEC Section 250.50 covers grounding electrode systems, which include ground rods, ground rings, and other grounding electrodes. NEC Section 250.52 specifies the types of grounding electrodes that are permitted. NEC Section 250.53 covers the installation of grounding electrodes. NEC Section 250.66 covers the sizing of grounding electrode conductors. NEC Section 250.166 covers grounding requirements for separately derived systems such as generators. The NEC also addresses the issue of stray voltage, although it does not use that term specifically. The code requires that electrical systems be designed and installed in a manner that minimizes the risk of shock hazards and other electrical hazards. This includes taking steps to prevent stray voltage from reaching levels that could be harmful to people or livestock. The Institute of Electrical and Electronics Engineers, or IEE, also publishes standards related to grounding and stray voltage. IEE Standard 142, also known as the Green Book, provides recommended practices for grounding and bonding of electrical equipment. IEE Standard 519 provides recommended practices for harmonic control in electrical power systems. Harmonics can contribute to voltage imbalance and stray voltage. In addition to these standards, there are also various industry best practices for managing stray voltage. These best practices typically involve a combination of proper system design, installation, maintenance, and monitoring. Some utilities also offer programs to help customers identify and mitigate stray voltage problems. Finally, consider the potential impact of electrical noise on the system. Electrical noise, also known as electromagnetic interference, or EMI, can disrupt the operation of electronic equipment and contribute to stray voltage problems. Electrical noise can be generated by a variety of sources, including motors, generators, and electronic devices. To minimize the impact of electrical noise, it's important to use shielded cables, filters, and other noise suppression techniques. Also, ensure that all equipment is properly grounded to provide a low impedance path for noise currents to return to the source. Implementing a comprehensive approach to grounding, bonding, and noise suppression can help ensure the safety and reliability of the electrical system and minimize the risk of stray voltage problems. Remember to consult with qualified professionals for specific guidance on your situation.